In conventional titanium alloys, you won't usually see more than 6 weight% aluminium additions, since second phases start to form that are generally unwanted. However, when you make an alloy that is nearly half and half titanium and aluminium, you create a material that has desirable high temperature properties, but can be a little awkward mechanically. These alloys are known as titanium aluminide intermetallics. In this lecture, I will give an overview of these alloy systems and their applications. I will discuss their complex phase transformations, talk through their typical microstructures, cover some of their deformation mechanisms, walk you through common thermomechanical processing routes, and end on recent developments in grain refinement. To date, titanium aluminide intermetallics, or just titanium aluminides, written as TiAl, are very light, stable at high temperatures, but have limited applications as these alloys are extremely brittle and difficult to process. At the moment, there is much more research to be done on these alloys to develop an advanced knowledge base, such as that which exists with titanium alloys. Titanium aluminide alloys offer significant benefits over other alloy systems, particularly in aerospace applications. They are significantly lighter than titanium alloys and are dramatically lighter than nickel-based superalloys. They have a specific elastic stiffness 50% higher than other materials used in aerospace. They have high tensile strength and creep and corrosion resistance in the 600 to 800 degrees C range, as they have stable microstructures at these temperatures. And finally, they are more burn resistant when compared to titanium alloys. These qualities make titanium aluminide alloys an excellent choice for aerospace applications such as turbine blades. The most famous application of titanium aluminides is the low-pressure turbine blades in the GEnx engine on Boeing's 787 aircraft in 2011. However, there are other commercial applications of titanium aluminides. For example, a gamma titanium aluminide alloy has been used for the casing of the Omega Seamasters diver's watch. Though at a price of £40,000, there isn't likely to be a trend of titanium aluminides in watchmaking. So, what are titanium aluminides? Titanium aluminide alloys are titanium alloys containing typically above 40 atomic % aluminium and small additions of other alloying elements, which are usually beta phase stabilizers. Similar to two-phase alpha plus beta titanium alloys, titanium aluminide alloys contain multiple phases designed to attain high strengths. However, they are much more complex than titanium alloys. Titanium aluminide alloys typically contain a combination of the TiAl phase, also known as the gamma phase, the Ti3Al or alpha 2 phase, and the B2 or beta 0 phase at room temperature, but the regular alpha and beta phases found in titanium alloys do form at very high temperatures. An example phase diagram of the Ti43Al atomic percent, 4 niobium, 1 molybdenum, 0.1 boron alloy system is given on the right of this slide, where the x-axis shows increasing mole fraction of each phase, and the y-axis is the temperature from 600 to 1700 degrees C. Below around 1100 degrees C, the material is dominated by the gamma and alpha 2 phases with a small amount of B2. Above 1100 degrees C, there is a transition to the alpha phase, and above 1400 degrees C, the beta phase starts to dominate. Remember that in titanium alloys, in Ti64 for example, the alpha exists at room temperature up to about 980 degrees C, where it transforms into the beta phase. There are other phases typically found in titanium aluminides which serve other purposes, like the TiB2 titanium boride phase used in the example alloy system here for grain refinement. The Ti3Al alpha 2 phase has an ordered hexagonal DO19 structure, which is shown on the left of this slide. When compared to the titanium hexagonal close-packed crystal cell, shown in black on the diagram, the DO19 TiAl cell is much larger, and many more atoms need to be included in the cell to capture the atomic ordering pattern. The TiAl gamma phase has an ordered tetragonal L10 structure, which is shown in the center image. The titanium and aluminium atoms are stacked in alternate layers in the cell's C direction. The beta zero phase, like the common titanium beta phase, has a body-centered cubic structure and differs only from the beta phase by having an aluminium atom at its center, and so it is also an ordered phase. The alpha phase in conventional titanium alloys has half the A crystal cell value of the TiAl alpha 2 phase, but a similar C parameter. Its C over A ratio is about 1.04, whereas for the alpha phase it is about 1.58. The DO19 alpha 2 structure has aluminium atoms in positions representative of the titanium atoms in the alpha phase cell, with titanium atoms filling all other DO19 cell positions. The gamma phase has alternating layers of titanium and aluminium atoms that create variance in the A and C lattice parameters. This phase is present from room temperature upwards and can survive until the melting temperature, depending on alloy chemistry. The ductility of the gamma phase is poor up until about 600 degrees C. In titanium-aluminium binary alloys, the beta phase does not form with aluminium additions above around 45 atomic percent. So in titanium aluminide alloys, which contain over 45% aluminium, the beta phase does not form without further alloying. The beta phase forms at very high temperatures directly during solidification, but as the material cools, it transforms to the ordered beta zero phase, which always incorporates an aluminium atom at the cell's center. With the addition of beta stabilizing elements, like in beta stabilized titanium alloys, beta zero can survive as a metastable phase in the room temperature microstructure. Titanium aluminide alloys with beta stabilizers, so-called beta solidifying alloys, have reduced texture strength, increased hot workability, and limited macro segregation. A typical solidification and phase transformation path of a gamma titanium aluminide alloy, one that only has gamma and alpha 2 phases remaining at room temperature, is shown on this slide. The phase transformation steps marked on the phase diagrams on the left are shown schematically on the right for a typical microstructure evolution. In step 1, the material starts to solidify at 1550 degrees C from the liquid into the beta phase, and at step 2 only the beta phase is present when solidification is complete. When the temperature drops below the beta transverse temperature at 1400 degrees C, the alpha forms similarly to how it forms in titanium alloys, which, at the cooling rate presented here, nucleates at the beta grain boundaries and grows inwards. As always, the alpha and beta are related by the Burger's orientation relationship. At step 4, when the temperature drops below the alpha transverse temperature, the alpha phase decomposes into alpha and gamma phases, where the gamma phase shares the Blackburn orientation relationship with the alpha, which is written in the bottom right of the slide. Finally, below 1100 degrees C, the alpha transforms into fine gamma plus alpha 2 lamellae. After the material has solidified and cooled through the various phase transformations, thermomechanical processing can be used to produce a variety of microstructures. This slide shows two examples. On the left, the material has been simply heat treated in the alpha phase field and quickly cooled, producing a fully lamellar microstructure of alpha 2 and gamma. The material on the right has been hot deformed and heat treated to produce an equiax microstructure of large primary gamma grains separated by alpha 2. As mentioned previously, beta stabilizers like molybdenum and niobium can be used to create beta solidifying titanium aluminide alloys, which allow the beta and beta zero phases to exist in a metastable condition at room temperature, along with the alpha 2 and gamma phases. The phase diagram on the right demonstrates this beta stability with increasing molybdenum additions to a Ti 48 atomic percent aluminium alloy. As the material cools, The molybdenum additions allow the beta and beta zero phases to remain below the alpha transist temperature to create an alpha plus beta zero microstructure, as well as gamma plus beta zero microstructure at lower temperatures. Therefore, with the correct heat treatment, alpha 2 plus gamma plus beta 0 microstructures can be produced, like those shown in the micrographs in the bottom left of this slide. Here are further examples of the variability of microstructures available through heat treatment of beta solidifying titanium aluminide alloys. Microstructure A on the left, in the as-cast condition, contains gamma grains, coarse alpha 2 and gamma lamellae, and large particles of beta and or beta 0. Microstructure B, heat treated for an hour at 1230 degrees C in the alpha beta gamma phase field and air cooled, contains fine alpha 2 and gamma lamellae, large particles of beta and or beta 0, and some alpha lats. As the heat treatment temperature approaches the gamma solvus, that is, the alpha plus beta phase field, the alpha 2 plus gamma lamellae dominate the microstructure, only separated by an increasing content of beta and or beta 0 phases. Due to the different scales of the multi-phase features, these different microstructures are capable of producing a range of mechanical properties, and so allow a great deal of material customization through heat treatment alone. Using electron backscatter diffraction, we can more confidently identify these phases, as shown here in a beta solidifying titanium aluminide alloy. However, due to the fine-scale nature of these microstructures, picking out the fine detail with this technique can be challenging. Let's move on to the deformation mechanisms. Slip in the gamma and alpha 2 phases are different than in the titanium alloy alpha phase because of the substitutional aluminium atoms in the crystal cell. For example, in the cell diagram of the gamma phase in the bottom left of this slide, titanium and aluminium atoms alternate in layers. So for a C plus A type dislocation, titanium atoms slip into positions that best fit aluminium atoms and vice versa. That is, moving the atoms into higher energy positions. If a dislocation causes one of these high energy atomic arrangements to form, it is called an antiphase boundary. The ordering of these phases results in easy and hard slip directions. In the gamma phase tetragonal cell, 110 slip directions should be favoured, but due to the atomic arrangement, there are 4 easy slip directions involving only titanium atoms, and 2 hard slip directions involving both titanium and aluminium atoms. It's actually more energetically favourable for super dislocations to occur when slipping in these hard directions. This is where atoms move 2 atomic positions for a single dislocation. That is, titanium atoms move over the aluminium positions and settle in the next titanium slot. The alpha 2 phase DO19 cell similarly has anisotropic slip. It tends to slip on the prismatic planes in the 112 bar 0 directions, but again, there are easy and hard slip systems due to the atomic arrangement. In general, this slip anisotropy in the gamma and alpha 2 phases causes a significant reduction in ductility at temperatures below around 600 degrees C and makes processing titanium aluminide alloys problematic. Like titanium alloys, titanium aluminides require thermomechanical processing to break up large cast grain structures and remove elemental segregation. Due to the anisotropic slip activity and poor ductility, high temperatures are required for successful deformation processing, but the high reactivity of titanium aluminide alloys makes this challenging. The impact of temperature on elongation is exemplified in the figure in the bottom left of this slide. Below 600 degrees C, titanium aluminides, in red, have poor elongation compared to nickel-based superalloys, but above 600 degrees C, the elongation rapidly increases. For completion, the specific strength of the same alloys are shown on the right, demonstrating the superior high temperature specific strength of titanium aluminide alloys. The ductility of titanium aluminide alloys can be improved using beta stabilizers to introduce a relatively large fraction of ductile beta or beta zero phases, which can accommodate much of the deformation previously required by the gamma hard slip directions, preventing crack formation. For these alloys, the large as solidified beta grains need to be broken up because even though these grains transform into other phases during cooling, the texture is translated through orientation relationships to the room temperature phases, which creates mechanical anisotropy. To do this, thermomechanical processing is carried out in the alpha plus beta plus gamma or alpha plus beta phase fields, and a refined grain structure is produced through recrystallization. The micrograph on the top right shows the as-cast microstructure of a beta-solidifying titanium aluminide alloy consisting of gamma and alpha-2 lamellae and globular beta-0. And the bottom image shows the same alloy after hot deformation in the alpha plus beta phase field, producing a microstructure of primary equiaxed gamma grains interspersed between gamma plus alpha-2 lamellae and stringers of beta-0, similar to duplex titanium alloys. After the large cast grain structure has been refined through hot deformation, further heat treatment in different phase fields can produce a variety of microstructures. Here are some examples from a Ti 48 aluminium 2 chrome alloy, where 1 to 3 have been heat treated higher and higher in the alpha plus gamma phase field, producing near 100% gamma, duplex gamma plus alpha 2, and near gamma plus alpha 2 lamellae microstructures. 4 shows a fully lamellar microstructure obtained by heat treating in the alpha only phase field. Note, the phase diagram on the right is for the titanium aluminium binary system, and thus region numbers are approximate. There is, however, an alternative to thermomechanical processing. Inoculants can be used to refine the as solidified beta grain structure during casting. This is important since although texture is weakened through subsequent phase transformations during cooling after solidification, the orientation relationships do retain the parent beta grain structure, so each parent grain contains a microtexture memory of the beta texture and can behave like a single grain during deformation. If the parent grains are too large, the material is mechanically anisotropic. The mechanisms behind inoculant grain refinement are complex and won't be discussed in detail here, but essentially, inoculants provide heterogeneous nucleation sites, so new as solidified grains can nucleate more easily with a lower energy cost. Inoculants need to survive in the liquid melt pool to act as heterogeneous nucleation sites, and if enough are added, a microstructure of refined equiaxed grains can be achieved. In titanium aluminide alloys, boron additions are a popular choice. They form various titanium borides in the melt pool as nucleation sites. The effect of the grain refinement is shown in the images on the right, where the top image is a binary titanium aluminium alloy, and the bottom shows the same with 0.5 atomic percent boron added. If too much boron is added, the borides in the microstructure become large and are detrimental to mechanical properties, particularly for damage control. A recent development in the field of titanium aluminide grain refinement is isomorphic inoculation. Since hard particles like borides are detrimental to mechanical properties, alternative inoculants were sought that would blend with the microstructure better. A solution was found by using particles made from titanium aluminide variants with high melting temperatures that survive in the melt pool to act as grain inoculants. Furthermore, by using titanium aluminide variants, the crystal structures of the inoculants and the solidified material are so close that the nucleation step is skipped altogether and each particle simply grows with the liquid solidifying epitaxially around it. On the bottom left of this slide is an example of traditional inoculation, whereby the inoculant, labelled substrate, acts as a heterogeneous nucleation site for a new grain. The difference in lattice parameters A and B for the substrate and nucleus are shown here. For isomorphic inoculation, on the bottom right, the substrate and solidifying material both have the same lattice parameter A, and the energy cost for heterogeneous nucleation is skipped. Therefore, using isomorphic inoculation, a clean microstructure of refined grains can be produced during casting. The difference isomorphic inoculation can make to the cast grain structure is demonstrated in the images and graph at the bottom of this slide. However, the casting conditions must be carefully controlled to ensure survival of the isomorphic inoculants in the melt pool. And finally, it should be noted that titanium aluminide alloys are still in their infancy. Applications are currently limited and demand for these alloys is low. So, although research is ongoing, there is still much we don't understand about these alloy systems.